Laplace's equation in a disk. In this video, we're going to study Laplace's equation in polar coordinates. The problem is initially given in equations 1 and 2 as a boundary value problem in Cartesian coordinates. When we translate this to polar coordinates, the boundary value problem becomes that shown in 3 and 4. In equation 3, we have Laplace's equation in polar coordinates and the boundary condition given in terms of f of theta on the boundary when r equals rho. Here's a picture of the domain, and the important new point to notice is that r equals 0 was inside the region and the theta equals minus pi. We know this. What's not new is that we know the solutions immediately of the boundary of the ODEs that we're going to study, and in fact the eigenvalue problems will have a periodic eigenvalue problem and a Cauchy-Euler problem. So if we make the separation u of r theta equals r of r times theta of theta and substitute it into the PDE, we arrive at this equation. Dividing through by r theta and eliminating the term r squared, we end up with the equation at the bottom of the screen. We have a separated r equals a function of r on the left, function of theta only in the middle, and so both sides must be constant set equal to lambda. This leads to two ODEs. There they are, theta double prime plus lambda theta equals 0, and then the one on the right is a Cauchy-Euler equation. Now this problem we mentioned earlier is inherently a periodic problem, and we're going to have to consequently require periodic boundary conditions on the theta equation. So our theta boundary value, theta eigenvalue problem is given here at the bottom of the screen. This is the problem we've solved a number of times. In fact, the solution is given inside the front jacket of your book, and lambda equals 0 is an eigenvalue with eigenfunction 1. And when n starts at 1, the eigenvalues are n squared, and the eigenfunctions are given as linear combinations of cosine n theta and sine n theta. Knowing the eigenvalues, the r problem then becomes, well, we're substituting for, we have lambda is minus n squared, and we have a Cauchy-Euler equation with with a singular point at r equals 0. There's a typo in the book. It should be right below 6.5. It says x equals 0. It should be r equals 0. Consequently, we're going to require that our solutions be bounded. The solution and its derivative be bounded as r approaches 0 through positive numbers. Now the characteristic equation for the equation 6.5 is easy to see. It's r squared minus n squared equals 0. So that the roots are r equals plus or minus n, and n starts at 0. So let's see, when n starts at 1, we have a linear combination of r to the n and r to the minus n. And when n equals 0, we have a double root of 0, and the solution is a0 plus b0 log of r. So we have this general solutions of equation 6.5 for the two possibilities, and when we apply the boundary conditions 6, let's see. Well, in the solution r to the n plus c2 r to the minus n, we're going to have to discard make c2 equals 0 so that the solution doesn't blow up, and when lambda equals 0, we're going to have to eliminate the log r term. And so, in fact, the solutions to 6.5 that satisfy the boundary conditions are given at the bottom of the screen. For lambda equals 0, we have 1 for our solution, and when n starts at 1, it's r to the n. So now we have the two pieces of the puzzle. We have the solution for the theta equation given at the top, solution of the r equation given at the bottom of the screen, and we superimpose them in our standard fashion, and we end up with a0 over 2 plus the sum of r to the n times a linear combination of sine and cosine n theta. The last thing to do is to determine the coefficients a0, an, and bn, and we apply the boundary condition. We set r equal rho, And so the series becomes a series, full Fourier series for the function f of theta. And this is a very standard problem in the solutions given below in equation 6.8. So in other problems we'll encounter in chapter 6, we'll have variations of this where we have bounded conditions required and various forms of Laplace's equation will occur. We're going to study it also in cylindrical coordinates in three-dimensional space.